Okay.
Good morning.
Good morning. How are you?
I'm fine. How are you?
Oh, doing good. Doing good. Thank you.
Oh, you are in your house?
Yes. It's. I wouldn't be able to come so early to the class.
Hello, good morning.
Oh, good morning, Sarah. You were able to meet on Friday. I saw your face was unhappy when I told we meet on Friday, and you mentioned Friday is not good option for you.
Yes, I can, but I have another meeting 10:30 a.m.
Oh, we'll finish earlier.
Uh,
This mm,
because I need to drive to that place for the meeting.
uh,
So
I'll I'll
if
try
we,
to finish within 1 hour or quicker.
oh, okay, that's fine. That's okay for me.
Okay, yeah,
Thank
thank
you.
you. So when everyone joins, I'll start sharing slides, and I summarized. I think it is on page 35. You do not need to look through the slides; they are boring. In page 35, I did summarize what I've learned about your project, so feel free to correct me. So Kea is doing some polymeric materials. If you send me information, I'll start looking forward to help you to do the project.
Mhm.
And Sarah, surfaces of clays. I do have some of them. Maybe you have something better, but I have a clear idea what is going on. So
Okay.
if we start thinking about project earlier and arrange our skills and whatever we learn towards the projects, it will be probably the best outcome.
Yeah.
Good morning, Boston. Thank.
Hello.
Hello. How are you?
Good. You?
Very good. Very good. Thank you.
That's good.
Um, Thank you for sending very detailed comments to each equation.
Oh, yeah. No problem.
It's a great skill. I don't know if you have like record of publications by now,
No.
but it will be very natural for you to write papers with the skill to explain each equation. It's really great.
Thank you.
In We'll wait a little if anyone else joins, and maybe I don't know. I need to share the link, or if you found it, then who else? Steven and
Lina.
Lina. Probably they'll find it. In slide 35, I try to summarize what I've learned. Oh, good morning, Lina. How are
Good
you?
morning. Good morning.
So you are in R1?
Sorry?
You are in the building R1?
Yeah.
I see it. You have a great office. I really probably it's very inspiring. Like to.
Yeah, this is the conference room in the
Oh,
building. It's not my office.
I wish one day it will be your office.
Thank you.
So I did summarize in slide 35 what I've learned about your projects. So for Boston, I didn't learn yet exact name of the semiconductor you are planning to describe, but as preparing ahead, you may inspect online for crystallography open database code. It's not a fish code. It's like COD crystal, and just type elements and try to find. They give atomistic models of all popular materials. And for Luna, I just found online you have a lot of papers. So I've learned what your research interests, and we may discuss which of your interests you may want to cover in the project?
Yeah, actually, the main project of mine is still not published. I'm working, preparing for publishing the main work. It's a single molecule binding spectroscopy.
Mm-hmm.
So we are working with ligands and receptors on living cells with their ligands. And I'm interested to see if we can do computational work on that, like I think docking molecular dynamics, something like that.
Mm-hmm. Yeah, we'll see. It should be possible.
Yeah, to predict the binding force maybe between the ligand and the receptor computationally.
Mm-hmm.
Yeah, or there is another possibility to do it's
With organic frameworks?
no, it's kind of simulating the number of receptors on the surface, and then designing the molecules with the ligands, then see like the coverage of or not the coverage, how these ligands bind to their to this surface. I think there is a name for that technique, but I forgot. I can review a little about that, and then I can tell you exactly what I want.
Yep. I would be interested to learn so that we plan efforts.
Yeah, because I saw many work in computational field for that experiment. So I'm interested if we can do that, it would be really great, matching my experimental results.
Excellent.
Yeah.
So about the slides and lecture, I'll just briefly cover in basic words, and then we'll go over slides. So last time we did discuss, and thank you all for submitting homeworks. We did discuss what is the molecule. So the molecule is collection of positive nuclei and negative electrons. They attract each other, they have kinetic energy, and we need to keep formulating it. And the first goal for today will be to recognize that quantum problem for such this large number of degrees of freedom is not possible to solve. Not because I do not have enough intelligence, but it is physically impossible for a human. And it is physically important for even advanced computer. So the problem is beyond any modern technology. So we need to, through today, goal number one, through today's meeting, we need to recognize that exact solutions for basically all molecules except like very small ones are not possible, and one needs to do several approximations. So it will be thought number one, idea number one. Idea number two that we will be pursuing for 2 or 3 lectures, there will be noticeable amount of equations, but the idea is simple, that in most practical situations, nuclear degrees of freedom, positions of ions, and dynamics of and eigen states, stationary states of electrons can be separated from each other. It relates to questions that Lina did ask at the end of the lab when everyone left. And it relates to the lecture delivered by Professor Kilina. So it is natural to believe that even in a big molecule, the ions are nailed down to the space and do not move, and we consider only electrons. But it is philosophically it is not correct. And in order to be general, we need to start earlier. We need to take into account that nuclei can move. And those of you who practice molecular dynamics immediately recognize like nucleus, motion of nucleus is major part of your science, right? So we need to discuss how to carefully, thoroughly, with all approximations and at the level of mathematical rigorosity, to split nuclear and electronic degrees of freedom. We need to discuss in which situations we can assume them independent, and how the equations will be simplified. So this second goal, it's very easy to say in words, but if we go through equations, it will take like 2.5 lectures, and we will return to this material maybe at the very end of the course. Okay, I think I'm done. Do you have any suggestions or questions about these aspects before I become like crazy and we'll go slide by slide without stopping? Okay, then I'll start sharing screen. And if you arrived to the stage where you have questions, please ask them by voice, because I may not see your faces and I can be too focused on the slides. So we are in the place of separating electrons and ions. It's like lecture number 3, and here is annotation. Let me see if I can do it. I never tried this annotation, but maybe it will. Okay, it works. No, it's better not to annotate. So in the previous lectures, we decided that we need to write correct software and correct hardware and compare outcome of the observables with experiment. And then there were a lot of ugly slides from myself and nice slides from beautiful slides from Professor Kilin about summary of quantum mechanics, eigenstates. And then you draw diagrams like this for finding the Hamiltonian, the total energy operator, for several examples of simple molecules. I looked through all of your homeworks and didn't find any errors to be corrected or discussed. You all are doing fine. We are in a good connection. So by now, maybe I can do instead of slide presentation, I can do this mode, and then I'll easily do annotations. A little technical problem, we'll resolve it. Okay, whew, I'm back to the normal. So we do have the Hamiltonian, which can be considered as a summation of 5 types of terms. And through the homework, you are experts in these terms. So there are terms related to nuclear degrees of freedom, kinetic and potential. There are terms related to the electronic degrees of freedom, and there is a cross term that connects both of them, correct? And one can connect them as 2 terms for kinetic and 3 terms for potential. So what are we doing with Hamiltonian? If you do have Hamiltonian, what should be done with it? And if you have ideas, feel free to share and raise the voice. Boston, what do you do with Hamiltonian in quantum mechanics?
That's a good question. You use it in the Schrodinger equation.
Correct. So basically, you can tell more, but I'm fine with this answer. So we plug the Hamiltonian into Schrodinger equation, where we do have this Hamiltonian, then we do have unknown this super big symbol. Wave function. And here is an important thing that I want to fill the gaps. The wave, and here is Eigen Energy. So energy, and here is wave function. So since our molecule consists of electrons and nuclei, we have so many electrons, and this curved brackets means that it is a set. It is like R1, R2, and so and as many electrons as we have in the system. And then we have a set of nuclear coordinates. We'll use uppercase, maybe upper indices, which means we have R capital 1, R capital 2, and so forth. So it is a wave function that has a lot of arguments. I do the same symbols, uppercase and lowercase for electrons and nuclei. So lowercase for electrons, uppercase for nuclei. The equation like this, I wouldn't say that it is ugly, but mathematically, I'm not looking forward to solve it. If there are more than 2 nuclei and more than 1 electron, it becomes really challenging problem. Like you probably have heard from your previous instructors writing books, and likely Professor Kivina did mention it, that there are about 5 problems in quantum mechanics that can be solved exactly, like harmonic oscillator, particle in the box, rigid rotor, soft rotor, and hydrogen atom, right? All other problems are solved approximately, with approximation. And this molecular Schrodinger equation for a molecule or any material, is not possible to solve exactly. I'm going to show a couple of arguments. Here. So let's look for first. Let's look for H2 molecule. So it has 2 electrons. It has 2 protons, and then each electron, each proton is a 3 vector, right? X, Y, and Z, which means, oh, good morning, Stephen. Nice seeing you Nice seeing you connected. And I did notice that you were connecting at 8 a.m. Thank you for being so dedicated. I was not able to join, but I saw you were connected. So 2 electrons times 3 degree of freedom for each electron, x, y, z, equals 6. 2 protons times 3 degrees of freedom for each coordinate equals 6. It means our wave function will depend on I do not have energy to write it. X1, X, Y1, Z1 for first electron. X2, Y, I'm already tired. Y2, Z2 for second electron. X uppercase 1, Y uppercase 1, Z uppercase 1 for first proton, X2, Y2, Z2. So not even solve, just list all independent variables is a hard task for me. Maybe for you it will be a little easier, but it's you see, it is a challenge. Now let's just consider, probably insert an empty slide. Let's consider what will be the just a second. It's a little delayed in the zoom and editing mode at the same time. So if we have a little bit bigger molecule, for welding, right now most industries use electric welding, right? When welders open the masks, close the masks, and use contacts, and there are sparks, right? You maybe saw it when there is a construction of large buildings. In previous century, people were using the combustion welding when one uses like torch with flame, and it gives a temperature. So the main fuel for this torch welding was acetylene. So one of the simple molecules, C2H2. Now let's assess what will be the number of degrees of freedom for this molecule. So the number of nuclei will be 2 plus 2, 4, and times 3 degrees of freedom for each will be 12. For electrons, how many electrons does carbon have?
Electrons, it has 6 electrons.
Yeah, correct. Yeah, thank you. So 6 electrons times 2 plus 1 electron per hydrogen times 2. So total 14 electrons times 3 will be how many? 42. So we have 12 plus 42, which is like 54 independent variables. So we need to find function of 54 independent variables. It's a little bit challenging for calculus and for differential equations. I think you agree that we are not going to solve these problems exactly. Even if one does some tricks with coordinates, like subtract coordinates, solve problem in the center of mass, one can remove like 3 degrees of freedom. If one removes rotational degrees of freedom, one also subtract something like 3n minus 6. But still, it will be a huge, complicated problem. So you may already ask yourself why I'm in this class, why I'm listening to this instructor, why do I need this equation? If I want to solve practical questions, why do I need these stories about equations? In some sense, we do not need equations. In some sense, computers will solve everything for us. But when you will be in your professional life, when you will be writing papers, you need to explain which equations you are solving. Like educated, literate explanation what you did. So we still need to be aware of them. So at least later on, we will type some key equations in the Word and include in the methods section of your papers or thesis to explain which equation I did solve. What do mathematicians do, especially in the what do mathematicians do in the differential equations when there are too many independent variables? Maybe before asking this question, let me ask if any of you have taken differential equations in the past or taken now. Okay, super. That's great. Thank you. So if there are like if there is a one variable, it's fine. What if you have differential equation of two independent variables?
We can make separation of variable method, something.
Mm-hmm. Yes, yes. So we are going.
Depending on the...
It's not always possible, but at least we should try. So if there are too many independent variables, we should practice separating them and get, instead of one equation for many variables, get many equations for one variable or fewer variables. So several one-dimensional equations, it's only a wish. It will be probably not possible, but at least we should try to chop as many variables as possible. And the criterion for separating variable is that operator that acts on the function should be additive. It should be composed of some simpler operators that act on each variable separately. There shouldn't be products. Like if there are derivatives, like for example, you have a function of two variables, x and y. If the operator consists of derivative over x and derivative over y, if it is additive and it equals something, then variables can be separated. One can chop it on two independent equations. But if there is an additional term that includes product of derivatives and independent variables, then this separation will be impossible or very hard. So ideally, there should be situation when parts, when the terms in the Hamiltonian are additive, then life is quite easy, or at least reasonable. If there are some cross terms which include several variables together, it is harder. So in case variables can be separated, then independent function can be represented as product of some simpler functions of this independent variables. And this basic idea from differential equations should be practiced here in our case. So if we closely look on the molecular Hamiltonian, we will realize that most of the equations, most of the terms depend on one variable, or depend on variables of the homogeneous nature. If you look back onto the 5 terms in the Hamiltonian, each kinetic energy term depends only on one variable. It is good. Each repulsive term includes distances between ions or distance between electrons. So it is they refer to one or another domain of variables. So if there would be only 4 first types of terms in the molecular Hamiltonian, we would be able to separate electrons and nuclei. But unfortunately, we do have a bad guy. We have a term of electron-nuclear interaction that literally includes both types of variables. So if we would be able to remove this term or provide argumentation that this term is negligible, then our life would be substantially easier. We could practice separation of variables and get a smaller number of independent variables. So we are going to discuss details and opportunities if one can neglect this term or do some approximations that will help us still to consider electronic and nuclear degrees in a separate way. So this trick was historically first done by 2 individuals, Born and Oppenheimer, and this little copies from the Wikipedia or whatever textbook front page is maximally new about them. The only thing I can tell about Oppenheimer that if you visit city of Los Alamos, where the national lab is and where people were designing first nuclear bomb, the central street of the city has name of Oppenheimer Street because he was working there. So these gentlemen were able to help us today. They were able to suggest a way to separate electronic and nuclear degrees of freedom. So we are doing really good in time. I'm going to make a little, so to say, break, change gears, and remind all of you that at the end of the course we will be doing projects, and from time to time I will be reminding and showing which projects were done in previous years. So this is what was done when the course was offered for the first time. Some periodic polymers, metal organic complexes, combustion of gases, and from this year we were talking at the beginning. So for Boston, I want to learn more, but you can find your material in Open Crystallography database. For Sarah, we should discuss what should be. I'm kind of joking. It is my minimal understanding that you're trying to deposit either molecules of life or molecules of death, like on the surface of clay. And clay is like multi-metal oxide. For K, also I need to learn which polymer you are describing, so maybe chemical structure. And if it is crystalline, one can find the atomistic model ready for computations in the same place in the crystallography open database. If it is amorphous, we will need to draw it, and drawing molecules will be our next lab. Conjugated, so some polymers are so-called conjugated, and the simplest example, I'm going to flip 2 slides back. If there is a alternating single and double bond, which means electron can move freely along this chain, which means it will be a good conductor of electricity and will absorb photons of some frequency. So if the polymer that you are considering is conjugated, one can find a whole lot more interesting properties. So I'm yet learning about interest of Lena. You did tell me that you want to do absorption on substrates. It is only what I found in your like Google Docs that you were doing some metal-organic frameworks. And for Steven, we can discuss, but one of the possible things is to expand electronic structure on two-dimensional magnetic materials towards statistical treatment for finding observables of multi-configuration. So you can select some other project, but this one seems should unleash imagination of anyone who does deals with it. So just throwing in an opportunity. Okay, whew. Now I plan to finish within 24 minutes. So if you need to travel or to other places, or you have some other classes, will be done. So next slide will be quite easy, but it will be the main idea of the next 2 lectures. I will be telling it again and again in different ways with more detail, but here is the summary. By matter of fact, all ions are substantially heavier than electrons. For example, the lightest nucleus, proton, has a mass of about 2,000 times bigger than mass of an electron. So it is approximately, well, something like this, 2,000 times. And due to this relation, momentum which enters into the kinetic energy, momentum of the nuclei is always much smaller than momentum of an electron, because and kinetic energy contribution from so electrons move substantially quicker than nucleus, even if the energy is comparable. And during the time when electron performs a lot of advanced types of motion, nucleus is has a lot of inertia and doesn't change its position substantially. So in many situations, one can assume that nuclei are frozen, or they are moving substantially slower than electrons. So during short interval of time, nuclei do not move and electrons move vividly. If this idea is accepted, then at least for short times, one can forget about nuclear degrees of freedom and solve only for electrons. But we should realize that it is not exact. It is an approximation, and it is important to discuss details of this transition. Why I'm going to waste your precious time and my maybe a little less precious, but still time. It will be done with the purpose of description of specific processes. So if there is a range of processes when nuclei move quickly, when one cannot neglect their motion. And the most bright examples are explosion and combustion. There are some other examples when you excite molecule with a laser, or if there is a quick adsorption or desorption, if there is a dynamic of adsorption and desorption, if there are chemical reactions. But if there is such examples as combustions or explosion, one cannot separate electronic and nuclear degrees of freedom. And no one of you mentioned that you really want to describe combustion, but I want to keep your hands untied, so that if you decide, or if in the future you need to do something that needs connection between electronic and nuclear degrees of freedom, we can do it easily. Another example where connection between electronic and nuclear degrees of freedom is needed is the project of Boston. And can you guess why you may need connection between electrons and nuclei? So to my understanding, interests of Boston are in photovoltaic. When there are two pieces of material, like P and N doped, and upon photoexcitation, charge travels across. So when charge travels across, the energy, maybe I'm not presenting it in a smooth way, come a little bit back. There is a big lie of quantum mechanics. In postulates of quantum mechanics, one tells that if system is prepared in the certain eigenstate, it will stay there forever, right? But Mother Nature teaches us otherwise. If you were dealing with spectroscopy, even with common sense, without any equations, if you excite molecule, it will stay there only a certain lifetime, certain duration of time. Then it will either radiate photon or dissipate heat. This dissipation of heat is a key part of the photovoltaics. At the time when electron is moving across the interface, it also loses energy into heat. Without it, there will be no specific direction of photovoltaics. It will not work. So the energetically favorable direction of charge transfer is what makes photovoltaic systems to work. And since we need dissipation of heat, it means from electronic degrees of freedom, energy goes into nuclear degrees of freedom, which is not possible without their connection. So I clearly see that Boston may practice the content of next two lectures even during the class. Whew. 17 minutes left. And motivation is much more important than actual content and equations. Just remember last slide. The rest is there will be more equations, but not as important. So again, looking back on the types of terms in the molecular Hamiltonian. So everything related to ionic degrees of freedom. So kinetic energy and potential energy does include only nuclear degrees of freedom. So you can tell that it is truly ionic. If we take kinetic energy of electrons and electron repulsion, these terms also have only electronic degrees of freedom. So you can tell it is true electronic. And the nuclear to electron interaction, I do not like the word fake news or fake Hamiltonian, but it is not truly electronic degrees of freedom. It is not truly nuclear degrees of freedom. But if we accept that nuclei are nailed down to a space, then in some sense it looks like electronic. So I would better attribute this to electronic part rather than to nuclear. So if I need to put this electron to nuclear interaction either to one or another, it will be more electronic. And then I can combine these three terms and maybe call it effective electronic. Effective means not that it is very efficient, but in effect, it deals with electronic degrees of freedom. And now my technical goal will be to separate variables for this segment of operators that deals only with R capital, and this segment of variables that primarily deals with lowercase, with electronic degrees of freedom. It's not ideal, but it is something doable. Okay. So here is my plan. I'm going to find eigenstates of this, let's use good words, efficient, effective Hamiltonian that includes true electronic and electronuclear interaction. Let's find eigenstate of this Hamiltonian, and later, if we succeed in finding them, we will use these states as a basis to find solutions of overall big molecular Schrodinger equation. So this dependence on nuclei here is not real. It's more parametric because nuclei will be assumed not moving. So parametric means it is simultaneously there and not there. We will not. They will be like an index of a solution. Okay, we have no more than 13 minutes. If you are, like while running, a sportsman measures efforts, when to finish, like make few steps more and then relax. Yeah, these slides are quite ugly. So we are going to solve for this electronic pseudo-electronic degrees of freedom. And after we do obtain this solution, we are going, so I'm illustrating the word about basis. So the actual molecular wave function will be represented as superposition of this electronic wave functions as basis functions multiplied by weight factor, by proportionality coefficients, which at the same time will serve as wave function of nucleus. So this type of construction for overall molecular Schrodinger equation solution is most practical, and it is yet exact. We didn't neglect anything here. So we didn't separate variables, and formulating equation in this way doesn't bring us too far to the actual solution, but we are still on a safe side of being mathematically rigorous. Here is the same equation with a little less ugly writing. So this is our target solution of molecular Schrodinger equation. This is equation that depends explicitly on electronic degrees of freedom and parametrically on nuclear degrees of freedom. And this will be weight coefficient depending on nuclei. So the uncomfortable aspect in this equation is this summation. So if I can, I would find a situation when one can remove this summation and represent molecular wave function as a product of nuclear and electronic part. If I can do it, it is probably maximum what Born and Oppenheimer can help us with. So the goal is obtain product instead of superposition. Product in mathematical sense, not in like chemical multiplication. Okay, so we will try to build all mathematical steps needed to achieve this product in the lecture number 4, and we actually perform separation of variables in lecture number 5. So I think it is enough for today. And there is a little comment that those of you who were taking quantum mechanics do not need, but if you were taking it long time ago and not taken, let me bring up very little basic comment which will be auxiliary to the previous lecture by Professor Kilina. So the Schrodinger equation that we are writing down right now looks like differential equation that we write in a one line, correct? But practically, when equations are reformulated for computers to solve, it's very rare when one solves differential equation and find it as an actual function. Most typically, all equations are converted from continuous form into matrix form. And then Schrodinger equation, here I am giving an example of oversimplified form when there are only two discrete, when there is only 1 degree of freedom and it is represented only by 2 basis functions. So it is simplest matrix representation of Schrodinger equation. So I'm not showing the details of conversion from this differential form to the matrix form, but bringing up an idea that if one is able to convert differential operator into matrix and continuous function into a vector, then the all problems of quantum mechanics are formulated as eigenstate problem from linear algebra. Again, value problem from linear algebra. Let me check for my curiosity who of you were, please just sign if you were taken or not taken linear algebra in the past. No? No? Yes? Kia?
Professor, during my undergrad study, we did something, maybe I forgot.
Okay, that's fine. But linear algebra is the subject where one takes determinant of a matrix. You know the concept of determinant, right? Okay, and then the one multiplies matrices and finds their eigenvalues. Someone is typing. Let me check what is being typed. So basically, this is end of the lecture. Boston. I sort of taught quite a bit to myself, but no formal class. It is okay. It is okay. It is if you ever take it formally, there is a lot of writing, but not very lot ideas. So some people believe that linear algebra is the simplest possible math class. Well, many thanks for finalizing the schedule and being able to connect at this time. So I'm open to any questions, but if you do not have questions or if you have a rush to go to another class, meeting for today is done. Anyone is welcome to disconnect. I'll stay for a couple of minutes just in case if there will be additional questions, and you worked hard this week, so no homework for the weekend. Just accumulate energy and strengths, and have a nice weekend.
Have a good weekend, everybody.
Yeah. Thank you. Thanks, Doctor. Bye.
Bye.
Goodbye.
Bye.
Okay. Professor,
Yes.
You were just talking about that we need to show something like a project.
Yes. Let me repeat from the scratch. There will be 4 presentations that each attendee of the class will do. First 3 will be you will summarize what we learned in the labs.
Okay.
So we learn something new in the lab for like 2-3 weeks, and then on the week number 4, we split all materials from the labs on each class member, and you do like 5-10 minutes presentation teaching other class members.
Okay. So
for the last month,
mm-hmm.
We will apply skills from the labs to do some mini research.
Okay. So,
So
mini research will be based on my research work, right?
It is ideal if it will be based on your research. If you do not, if your research is secret, or you are, or you do not like, I can offer you some other problem. But ideally, you do not waste and do two projects. You do something for the class, and at the same time, it will be for your PhD project. So you do part of your main stuff and do computation of the material that you need to study during the class. And at the end of the class, you'll do brief paper and presentation about a result of this mini research.
Okay. So, Professor, my research work still actually, yeah, I'm still studying, reading papers. So hopefully next week I will discuss with these things with Professor Shah. Then we will figure out. Okay, that will be my research work. So still now, you wrote something amorphous and crystalline. I don't. Yes, I started to wrote these things, but I don't think so that will be. Professor said that my work will be based on Vitrimer, and Vitrimer is like
Can you type this word in the chat line?
okay, maybe. Vitrimer, also known as covalent adaptable network. I think you are familiar with covalent adaptable network.
Okay, I'll look what it is, and maybe we'll come to some additional suggestions. So let's wait until we read more and discuss.
Yes.
And this comment that I wrote about crystalline and amorphous.
Okay. Okay.
So it is applicable to any polymer. So
Yeah,
at
it's
temperature.
also applicable for this one also. When I read, I found that crystalline amorphous.
Okay. Okay. Yes, and I know that in the group of Professor Shah, there is a like skill that everyone in the group learns how to prepare dense packing of materials, and it will be really important skill that we can combine with electronic structure when you compress material to reach the realistic density.
The most important thing, Professor, I don't have. Actually, I never did simulation work, so that's why Professor said that take this course seriously. You will learn from this course the simulation work, and also Professor suggests me to register for CCAST. Then you will learn something from that one also.
So do not worry. For the class, all skills that are needed for success in this mini research project will be offered during the labs. You do not need any preliminary skills.
Maybe during the lab, from next week, I will try to be in person because last time I'm trying, but that some problem happened in the laptop. So it will be better if I stay in person.
Yep, you're very welcome to attend in person.
Okay, Professor. Bye.
Bye. Have a nice weekend.
Have a nice weekend, you too.